Okay, so hello everyone. Thank you again for coming to today's webinar. I know it's been a while since we've had an offering in the series. So today we're very fortunate to have three panelists to tell us about actual programs in data science. And so we've been looking at what individuals have been doing in lecturing. We've been looking at ethics. We've looked at tooling. And so this time round, we'll look at full programs in data science and see how we might learn from that in a physics context. So with that, we'll get started. I'm going to ask you to hold your questions until the end. And Neil will post a link in the chat for a Slido so that you can capture your questions there, and we'll get to them during the panel discussion period. So with that, we'll get started, and we'll start with Sarah Stone. So Sarah is the executive director of the University of Washington's eScience Institute, the campus hub for data-intensive discovery, where she oversees operations and planning and designs and implements programs and partnerships. Stone is a co-founder and former director of the Summer University of Washington Data Science for Social Good program, which is how I know her through my work with DataKine. And her program partners with student fellows from across the country with project leads from academia, government, and nonprofits to work on focused collaborative projects for societal benefit. She serves as the co-director for the new Scientific Software Engineering Center at the University of Washington, which is building a team of software engineers to work with domain researchers, computer scientists, data scientists, and others to develop high quality, sustainable software for cutting edge research purposes. So with that, Sarah, would you like to tell us a little bit about the program at U Washington? And for the audience, please, ask your questions, and thank you.
Yeah, thank you. Thank you for the invitation to join you, and it's a real pleasure to be here. I'm going to be talking, and thank you for the lengthy introduction. I didn't know the whole thing was going to be read, but I'm going to really focus in today because I know that's kind of the topic is around the data science education programs at the University of Washington. But I'm certainly happy, please reach out to me if some of the other things that were brought up in that intro are of interest to you. eScience, we do a variety of different types of things. And so I'd be happy to touch base with anybody about some of those other items in the future. Let's see, I'm just going to go ahead and share my slide deck. Does that look like it's working for everybody?
Perfect.
Okay, great. And are you getting background noise? I have my window open, but that's not coming through, is it?
Sounds perfect.
Okay, great. It's been very hot in Seattle, which we don't usually say. It's an unusual phrase for us to put together, but here we are. So thank you. So I'm at the University of Washington eScience Institute, and I serve as the executive director for the organization. And I always like to just start by focusing on our tagline because it's a succinct way to talk about our mission, which is advancing data-intensive discovery in all fields. And so different than some of the university-based data science institutes that have been popping up across the country, or I'd say the way that we relate to those is that we're not focused on particular fields. We're also not focused on a particular part of the data science workflow. We're interested in engaging with all different parts of campus and working with people, even if they don't have big data, but they've sort of outgrown their spreadsheet and they may just be dealing with the data cleaning and data wrangling and not necessarily moving into like advanced AI spaces. We sort of cover that full trajectory. So to say in a lot more words, what we're about is really empowering researchers and students in all fields to answer fundamental questions through the use of large, complex, and/or noisy data. And the empowering, I think, is really important. So we are focused on meeting people where they're at in terms of their technical background and designing programs that are going to meet the needs both for students and for researchers on campus. And a lot of what we do, and I'll get into this at the very end. And again, these are things that I'd be happy to answer more questions on, or offline if that feels like it's less the focus of today's conversation. But a lot of what we do is community building activities to support and make connections for people across campus. So our role is really, in three areas, like many parts of the university. We're focused in education, in research, advancing research, and in community building. What I'm really going to focus on today is the role that we've played in developing data science education at the University of Washington. And I'm going to divide that and focus primarily, again, hopefully I'm meeting the context of this group correctly, but I'll focus mostly in my remarks about the formal curriculum and the role that we've played in that. And then I'll just touch briefly on informal training programs that we've developed at the end of the talk. So just again, like to provide some framing, because I think when we think about data science lives in various, depending on your university, it lives in various different parts of the university. Some places are building out schools of data science or colleges of data science. It might be a grouping of different departments that are coming together and thinking about data science. It might just be within your own department. So I think it's helpful to have some framing of where I'm coming from and situated. So the eScience Institute is an institute, so we're not a department, school, or college. We sit outside of that structure. And that means that we don't have our own faculty lines. We don't have our own formal courses that we're offering through the institute. We report broadly to the Dean of Arts and Sciences, Engineering, and the libraries. What we have been able to do, and what is advantageous about this structure, is that we are a neutral player. We don't stand to gain anything by developments in data science formal curriculum. No money flows to us from those types of avenues. And it allows us to foster conversations across departments that may not be as willing to talk to each other, or, for example, at our university, CS is a powerhouse. And, if this was looked at, if data science education was coming out of CS as the lead, I think it would have been much harder to get partners to the table and to really foster a collaborative conversation. And that'll make more sense when I move into the approach that we've taken. But what we were able to do as a neutral player is convene a data science education working group. And this goes back to about 2013, 2014. And that comprised faculty from more than 15 different departments who were really interested in looking at and thinking about what should data science education look like for the campus at the University of Washington. And we put our stakes in not thinking of data science as its own separate discipline or department, but really approaching data science as a suite of methods and tools and technologies that are valuable regardless of what disciplinary space you're in. And so when this working group was really thinking about what are the key, like creating a framework, what are the key components of a data science education? And then how would a department instantiate that framework? Again, that'll make a little more sense as I dive into the details here. I'll just note that, this initial education working group now goes back about 10 years, and you'll see what came out of that group, which has been developing really since then. More recently, because we're really seeing a push for a focus on AI. And so now we're thinking about AI education. And we have an AI education working group trying to understand, is AI education substantively different from data science education? Where do they deviate? Where do they overlap? What does that look like across different departments? So we're kind of doing the same thing now, but looking at AI. So putting it all on one slide, this is what data science looks like. Data science formal curriculum looks like at the University of Washington. When we started approaching this, again, going back to about 2013, we started at the graduate level. And that was probably two reasons. We had a funded IGERT from NSF, a big data science IGERT. And so that provided some of the sort of funding and impetus to create the structure. Also, just to be frank with you, graduate education is often a lot more flexible, and so it was an easier place to start. And so the way this works, well, I'll just go through. So at the graduate level, we have two what are called data science options. You could think of this as a specialization, but it's owned by the home department and instantiated by the home department. So a student is still getting a degree in their primary space, but they have this option, which is transcriptable, meaning it shows up on their transcript when they graduate as a specialization in data science. The initial option we did at the advanced graduate level. It quickly became clear that the advanced data science option is kind of the highest level courses, and I'll show these to you in a minute, across these primary areas of data science. For a lot of students, depending on their department, it was hard for them to meet all the prereqs to get in those highest level courses. And so then we created the standard data science option at the graduate level, which again takes that same framework, but has a lot more flexibility for the department to bring in courses that are most relevant for their students, and to include courses that aren't sort of the highest level course in that area. As we built those out, we really wanted to bring that same structure to the undergraduate curriculum. And so we developed a framework for undergraduate data science options. These work the same way. Again, it's a specialization. The home department owns it. The students are still in their department, but they're getting this option or specialization in addition to their primary degree. We found, and again, I'll show you the details of those, that the data science option at the undergraduate level worked well for methods departments. And by that, I mean, departments where students were already taking a lot of kind of the primary coursework for data science. So they were already doing some programming, they were already taking machine learning and stats. And those departments, it was fairly easy to instantiate an option because their students were already taking some of those courses. It wasn't a huge number of additional courses. For departments that were not methods departments, it was much harder. As you all know, I'm sure the undergraduate curriculum can be so impacted. And so departments, even in STEM fields like biology, were really struggling to figure out how to fit the courses in for students to add a specialization or an option in data science. And that created the impetus for a data science minor. And so the data science minor is sort of the newest piece of this puzzle. And that allows, again, across campus students to pick up data science skills. The data science minor was particularly focused and targeted towards students in the social sciences, arts, and humanities. Again, with this idea that students in the more like the engineering space would be more likely to do a deeper data science option. So I know that was a lot, and this is a lot on the slide. So what I'd like to do now, I'll just step through these different options so you can kind of get a feel for what they look like. I'll try not to belabor that too much because, if you want to get into the nitty gritty, all of this stuff is actually on our website, or I'm happy if you want to reach out to me, or that can come out in questions. I guess the last thing I'd say on this, we also have a data science master's, a professional data science master's, I think like many universities do. This was also, the structure for that was also put together by an interdisciplinary group and is governed across 6 departments on our campus. Okay, I think I've kind of already talked about this. So these data science options, as I mentioned, are based on a framework that was agreed upon in this broad group of, in the data science working group. And the idea is, so if I'm just taking an example, and I use oceanography because that's my background, a student in the graduate program so you'd still get, say, a PhD in oceanography, but it would be with an advanced data science option if they went that direction. The process for this, for creating an option, and again, this may or may not be available in your university, the structure, but the department faculty, so we work with departments to put together an option and to make sure it fits in the framework that has been agreed upon. And then departmental faculty vote to add that option. And then either the graduate school or the undergraduate curriculum group, does the review and gets input from campus to ensure that these aren't, that this is going to work, because in many cases for data science options, I'm sure this is true for you all too, that students are taking courses outside of their home department, at least to some extent, to fulfill those requirements. Okay. So what does this look like? So at the highest level, so the advanced graduate data science option, we think of this, we made this distinction between coursework for tool builders versus tool users. So again, the idea with the advanced graduate data science option is this is the highest level courses in these categories, which you can see here: stats, ML, data management, and data viz. And these are classes that do have a lot of prerequisites. So it's a very intensive course load, and it's really, again, designed for people who want to be data scientists or really be the tool builders in their disciplinary space. We have a joint seminar series that all these students participate in that covers topics across a breadth of different disciplinary application spaces, as well as topics like ethics and responsible ML. Let's see, and this is currently offered in 14 different departments or units on campus. The standard graduate data science option, you're going to see a lot of the same categories, but in this case, there's a lot more flexibility about which courses they take. So they're still going to do, stats, pick 3 out of 4 courses in these different areas, but they don't necessarily have to be the highest level courses. And we've certainly seen a proliferation, for example, of machine learning courses across different departments on our campus. And we help students find, we keep a large list of all the courses that are available for students across departments in data science, so that they have an idea of how to move through these different programs. This allows a lot of flexibility. So for example, again, I like to always go, and I know you're all physicists, I should give physics examples, but I'm probably less qualified to do that. In oceanography, for example, a data visualization class might be about ocean modeling, which is really a critical, a critical kind of tool or practice to understand as an oceanographer. A data visualization class for a computer scientist might look quite different. And what this framework allows is that kind of flexibility so that students coming out of a program have the coursework that's most meaningful for the direction that they want to go in the future. And this standard graduate data science option is offered in 16 different departments, and many of those are overlapping with the advanced. So a number of departments offer both of those options. This has been supported and allowed us, I think, to be particularly good partners for things like NRTs or T32s, because those programs are departments that are putting together those kinds of proposals can leverage this existing structure. My understanding is I think this is more of an undergraduate focus group. And so I'll dive into the undergraduate structure. Again, we have the data science option we put together at the undergraduate level. And again, they're getting a degree in a primary discipline, and that appears on the transcript. And let's see, and part of when we were developing the data science options, that also led us to create a lot of introductory courses for students that are part of the data science option that don't have any prerequisites. And so some of those are included down here. So that included building out a data and society course, which was great for sociology because that's a very sought after course, and that allowed us to form a nice partnership across campus. And brings a lot of students into that course, which is advantageous for them. We have an introduction to data science course, which involved a very complex negotiation between 3 different departments. This rotates between departments so that the funds that come in for that course are shared. And then also the development of other types of intro programming classes for students who don't have any previous programming experience. If we look at the undergraduate option, so it has a programming requirement, so a course in programming, a course in machine learning, a course that covers privacy, security, ethics, and society. It can be that data and society course that I mentioned on the previous slide, but there's also, these courses have been coming up in many different departments across campus, so it doesn't have to explicitly be that course. And then 2 out of 3 courses covering data management, data visualization and communication, statistics and probabilities. And then departments also have the option either to slot in department-specific courses in any of these, categories, or to add additional courses if they feel like it's really critical that students in their department have, some particular course. This is offered in 8 different departments. As I mentioned, these are primarily methods departments. So, CS, stats, applied math, but we have had some more applied departments. Atmospheric sciences has an undergraduate option, for example. The last major program I'll talk about is the data science minor, and this is our most recent addition to the curriculum. And this was launched in the fall of 2020, and it already has over 400 students. I think we've probably reached, given that with students graduating each year, about a steady state for this program. As I mentioned, this is really trying to help democratize data science education and really attract students in the social sciences, arts, and humanities to picking up data science skills, and to really be not so much to get trained and be able to go into the field as data scientists, but because we were seeing this sort of emergent need for data translator roles. And so having this kind of expertise in policy, design, social theory, and ethics around data science is a growing need and skill that we see particularly in our local tech industry. And so this program is really meant to help give students that kind of training. And it consists of a mix of courses and data skills, which would be things that we might think about, like programming in Python, as well as data science studies, which is much more of understanding the context in which data is being used, and maybe the political or ethical framework for that data. This it currently involves over 20 different departments on campus. That means it includes courses from over 20 departments, and there's a way for departments to apply to add new courses to the minor. And again, it's been really helpful for the eScience Institutes to serve as a home for the minor, because again, that didn't look like one part of campus was going to own and get to control this minor, which I think, again, would have made it much harder to push this through and really have the collegiality across departments. And we've been very fortunate that this, the data science minor funding was associated with bringing on some new faculty lines. So we had 3 new faculty shown here, Karen, Anna, and Mia, covering sort of social sciences and humanities spaces. We have 3 new faculty who will be starting in the fall, also to build out the coursework for the minor. Lastly, just in my last minute here, hopefully I'm doing okay on time. Oh, I'm over time. I'm just going to say we also do what the eScience Institute then does. What I've shown you is a lot of what's happening, and we've helped to facilitate in different parts of campus. We have a number of core programs that help people sort of in the informal data science training space to pick up new skills. And so some of those are listed here. Again, I'd be happy to talk about these in more depth with any of you. And I just would like to say thank you.
All right, thank you very much.
Yeah, you're welcome.
All right, so I think I'm going to have to be a little bit more judicious with introductions. So next up, we will go with Jim. So James Hickman is an associate teaching professor in the data science and analytic program at Georgetown University. He holds a PhD in computational physics from George Mason University. His research experience includes applying classical atomistic simulations to material science and condensed matter physics problems. And he was an NRC at NIST. Yeah, I have to say, go NIST. That's where I currently am. And so I'm looking forward to him telling us about the data science program at Georgetown, and yeah, how he's finding it there, and how it might be useful for those in our community to.
All right, so I'll start by sharing my screen. So I'm going to explore our website instead of going through a slide deck. I'll share this in the chat. This is the website that I'll be referencing. Collect my Zoom windows. Everyone can hear me well, and you can see my screen. All good? Yeah.
Yeah, it looks good. You're not full screen on the presentation yet, but
You can see the website though?
yes.
Okay. Hide my controls. All right, so I'm actually just going to run through the website instead of doing a slide deck. I'll just sort of introduce it through here because most of the content is provided here. So, and it's nicely organized. So I am part of the data science and analytics program at Georgetown University. So this is one of our master's programs. There's a second data science master's program in the McCourt School, focusing on data science for public policy. So this is, as the name suggests, more policy oriented. I'm not in this department, so I'll focus more on the data science and analytics department, which is more technical, I would say, more code focused, more highly Python, highly R focused, and so it's more on the technical side of things rather than on policy oriented. We do have so we are a master's program. We also have a 4+1 program for undergraduates, which is for Georgetown undergraduates. So it's probably not as advantageous for non-Georgetown undergraduates, but as a master's program, it's a useful option for undergraduates. I sort of see in our program, we are more on the technical side of things. I do see our program as a very good fit for sort of any STEM major. So we just went through our application reviews in February, and we had quite a lot of STEM majors. Actually, not as many physics majors as you'd expect, but a decent proportion. So we are highly interdisciplinary. We're getting everything from finance and marketing majors, business majors, some data science majors, but more coming from, again, STEM disciplines. I view the program as sort of is an excellent fit for someone coming out of, again, some sort of STEM major. So my background is in physics and applied mathematics, and I would have been very, very happy with this program coming out of undergraduate. So my undergraduate degree was in physics and applied math. On the math side, I didn't really see, I mean, this was many years ago, or about 10 years ago now, but I wasn't exposed to any of the things that we cover in our program. It was more focused on theoretical work, proofs, MATLAB, that sort of thing. Our program is much more applied, focusing on using machine learning tools, implementing them in Python, implementing them in R, and that sort of thing. So it's more of a kind of a technical program. But again, just seeing this coming out of a degree like a STEM degree, where you might not have seen a lot of these machine learning tools that are very useful, across very many platforms. So of course, this is our website, and we do have a very active. We're located in DC, right along the Potomac River, within sight of the Capitol and all of that. So we're right in the middle of DC. We have quite a vibrant community of our student community. We have game nights and meetups and all kinds of social events. So it's a great place to be. Very social atmosphere. These are just, you can look through this. These are some of our recent events. This DataKind DC, which is actually where I met up with William recently in November last year. So that was a very fun event, and you can see many of our students participated in that. And so we have a very active social community, relatively smaller. Not our cohorts are around 130 students per year. So we have about 200 total students. So it's an intermediate sized program. But again, so you can explore our website. Just look at our. Should start with, if you're interested, this is more sort of just background content. If you're I get the feeling that this is mostly targeted, this webinar is mostly targeted towards undergraduates, looking for future career paths. And again, I think this is an excellent choice coming out of a physics program, just to get a nice sort of to round out your resume, right? To kind of get away from, not away from, but to complement all of that theoretical work that you might have done during a physics program, right? Everyone, if you're in a physics program, right, you're aware of all the kind of level of rigor of, the undergraduate curriculum, all the electrodynamics, quantum mechanics, all that sort of stuff. It sort of might be refreshing for you, depending on what you want to do with your career path, to see something more in the applied space, right? So this is much more, just kind of messier data, right? We're dealing with just real world messier data. So I'll start with our courses. So we have, these are core courses and then various electives. So all DSAN students start with a boot camp in the summer. So it's a 2-year program. Some students finish it in 1.5. They'll take summer courses in between their first and second year to accelerate their progress and get done a semester early. So you can either do 1.5 or 2-year program. All students are required to take a boot camp, which is not, it's free. There's no credits associated with it, but it is required. We kind of quiz you on it at the beginning of the program to make sure that you're sort of up to speed with R and Python. So the boot camp really is just sort of a crash course to make sure that everyone enters the program proficient in R, proficient in Python. Our first course is data science and analytics, DSAN 5000. We just changed our number in literally like 2 weeks ago. So this used to be 501. So I apologize if I sort of revert back to the previous numbering, but this is sort of a just general introduction to the data science lifecycle. So our program is often highly project driven. So you're both doing sort of standard educational content, working through the standard, educational exercises, but also we'd like to really emphasize project driven assignments so that you can kind of take it as far as you want to, right? Like if you're doing something like MNIST, right? You can only take that so far. It's been done a million times, but we want to also provide students with the option to really, just choose something that they're interested in. So students do get to choose their own projects in most cases and really run with it, take it as far as you want and develop a really highly polished professional product. So this first introductory course, we go through just sort of the whole life cycle, data acquisition, API use, gathering data, cleaning data, different types of data, web scraping, moving into the EDA process. How do you visualize it? How do you sort through data? How do you deal with missing numbers? All the usual kind of standard stuff, and then move into sort of more analysis and storytelling. Like how do you make sense of the data, right? And how do you present that in a professional way? So that's a large part of our program is data storytelling and professional writing, professional data storytelling, and trying to kind of make sense of the data, not just look at it and analyze it and model it. I mean, that is part of what we do as well, but also how do you present that to stakeholders? How do you formulate that into a report? So that's a large part of our problem, our course, our program, excuse me. So these are the core courses that everyone takes. This is more, statistical modeling, trying to get everyone up to speed with, this is a first semester course, fundamentals of statistics. It's basically like an introduction to statistics. Well, not introduction, a bit of a kind of graduate level statistics course. Data visualization is a second semester course. So that's spring of your first year. If you're interested in the program, you'd be taking that. And that just goes through kind of the suite of all the kind of standard Python and R visualization packages. Some, of course, we touch on Tableau and Power BI as well, but more it's focused on reproducible methodologies, so more code-based. We try to steer away from point and click type applications because they're fairly straightforward. You can usually learn them pretty quickly. And we'd rather, focus on more advanced, Python and R based methodologies for visualization. So that's the second semester course. this is sort of our machine learning course, statistical learning. So here we go through, the standard suite of machine learning tools, primarily focused on supervised, of course, because most paradigms are supervised learning, but also, of course, the standard unsupervised learning methods as well, clustering, dimensionality reduction, all that sort of thing. And so this is sort of, just introduction to machine learning in Python and R. And then the final course, this is the final core course, I should say, is a fall second year. So this would be your third semester at Georgetown, is big data and cloud computing. So this, you get all the AWS, Azure, interacting with command line interfaces, shell scripting, pipe SSHing into remote clusters, that sort of thing. So this is sort of, remote distributed cloud computing, that sort of thing. So again, these are sort of and we emphasize that throughout the process. So again, it's quite a technical program. We do expect by the end of it, you should be kind of a pro at, the Unix command line, that sort of thing, and Python and R and that. So those are the core courses that everyone takes. And then we have quite a large suite of electives as well. So if you go back to the course descriptions, and if you want to learn more about the different trajectories and schedules, you can look again. There's a lot of information here. There's tabs for prospective students if you're interested. So this website does it should be useful for answering a lot of your questions and so on. Actually, before jumping to that, so we are a relatively, I would say, a relatively small department. We have just three tenure or non-tenure line teaching faculty, of which I'm one. Professor Nakul is one, and we have a few cross-departmental faculty, and we're getting one more faculty member. But a lot of our many courses are taught by our adjunct faculty. So we have a large collection of adjuncts that are working in the DC area. So DC is a great place to do data science. There's a lot of jobs. The federal government is hosted here and or centered here, and so we're able to kind of tap into that resource with a lot of our adjuncts. So we have a really great pool of adjunct professors. Trevor is one of our NLP experts, kind of focuses on works for the Department of Defense as a contractor. Amit works at AWS, and he just co-taught our data visualization course with him. And so Abhijit works at AstraZeneca, and so we have a large pool of adjuncts. And so a lot of our elective classes are taught by our adjunct faculty, as well as our core or as our full-time faculty as well. So you can look through this and get familiar with who is it, like what is the program, who are the people in the program. And so to go back to the course descriptions and the electives, so we do offer a pretty wide range of electives. I would say that one of our strong suits is NLP. We do have we have several adjunct professors that are really excellent experts in the field of NLP. So we have this is sort of shallow NLP techniques, and we're working on developing more concentrations for our students. So whether you want to go down sort of a traditional data science pathway or concentration, or a deep learning pathway where you get exposure to sort of a broad suite of data science tools, the usual TensorFlow, PyTorch, all that sort of stuff, and all the modern architectures, transformers, all the usual suspects, and then also NLP trajectory as well. So we're trying to sort of make different kind of choose your own adventure ways to sort of form your career and form which paths attract you. And in those core courses, we touch on all of these sort of topics. Like we touch on introduction to NLP, we touch on deep learning and that sort of thing. And so if early in your career at Georgetown you're sort of drawn to one of those disciplines, if you see NLP and you're like, wow, I really love this, you can kind of funnel down the NLP track. And or if you're more inclined to sort of a generalist deep learning perspective, you could funnel down the deep learning track. And so again, you can look through all of these. I don't want to go through them in too much detail, but again, a strong emphasis on NLP, time series as well, sort of financial marketing, financial modeling, and time series analysis, both deep and shallow methods, standard methodologies. Blockchain, Professor Nakul teaches various blockchain courses. So that's actually another emphasis that I should mention if you're interested in that kind of trajectory. We have courses for that. Again, lots of NLP courses and in kind of the whole spectrum of NLP, going from just cleaning text data, processing text data, getting it ready for analysis, forming vocabularies, and then piping, and then a whole suite of modeling tools, all the way again from sort of shallow deep learning methods, non-neural network, if you will, all the way up to, large language models. We're actually introducing a large language model course for spring 2024, taught by Trevor and one of our other adjunct professors that will, introduce students to like how do these large language models, ChatGPT, all the hot topics in hot topics that we're hearing at the moment. How do these work? How do we use them? And that sort of thing. So if you're interested in that, again, very good place to sort of get a crash course in NLP, which again is something I think you probably, wouldn't see at all in a physics curriculum, right? If you're an undergrad, I know at least in my undergraduate physics curriculum, I didn't even know what NLP was, right? And I probably should have mentioned that at the beginning. So natural language processing, machine translation, there's just dozens and dozens of tasks in the NLP space. And so, how we process language and how we learn from unstructured text data and that sort of thing. Storytelling, that's a huge part of our program. We really try to emphasize that in almost every class that, how do you, when you have your results, how do you, process them and present them to shareholders? And we do have a specific class for that, as well as something that we're sort of emphasizing every other class. Optimization, which is, that's a cross listing with the math department. So that's sort of a standard, optimization course, which is of course very important for, neural network training is essentially just an optimization problem. So if you want to understand how to train a neural network, it's good to understand the fundamental optimization paradigms, particularly gradient-based optimization. And so anyway, I don't want to go through it in too much detail, but really you can see we have a pretty large suite: computer vision, network analysis, deep learning. And this is actually a new course that I taught this spring for the first time. So we developed this just last spring. And this is an exciting course. It sort of finishes the triad. Machine learning is typically formalized as supervised learning, unsupervised learning, and reinforcement learning. So this is a new course that we kind of complete that triad. And at least from a physics perspective, I see this as sort of probably one of the more familiar courses, because there's that temporal element, like reinforcement learning is largely temporal decision making. So you have some sort of agent trying to make decisions in some sort of complicated temporal space that's moving forward in time, like playing a video game or something like that. And there's a lot of overlap with the physics curriculum in terms of, dynamic systems, maybe more so engineering curriculums, system control, automated control, and that sort of thing. But there's a decent amount. I would feel that coming straight out of a physics curriculum, some of this might feel kind of right closer to home than some other things. So again, this is would be a very nice course for physics, well, for anyone, but for physics majors, at least as coming from a physics background, I felt very at home in this space. Just sort of it resonated with a lot of the things I learned as a physicist, and so on. And some GIS courses, developing apps. Actually, this is something we also focus on in a lot of our courses. How do you get something like, you have all this data, you have all these modeling techniques, how can you spin that up into a public facing website to quickly share that with the world, or prototype for a company, right? Like that you might have an idea for a product, or your company has an idea for a product. How do we take that from raw data, modeling, app deployment? Like how do we show that to the world and get that up and running in a short time period? I should emphasize too, we heavily emphasize all the standard kind of professional technical working tool sets like GitHub. Every class we use, GitHub, and so we really enforce that heavily. So that's a big part of our program, just trying to enforce professional standards, which is part of the reason that having this adjunct population is so useful. They can kind of feed back into the program, telling us what they're seeing in their industrial experience, in the kind of outside of academia. What are they seeing as the most important use cases at AWS, at Microsoft, wherever they're at, wherever our adjuncts are at, and how can we feed that back into the program and constantly update it? That's, in fact, as a relatively new professor to this program, that was one of the hardest things that I've found teaching, is just constantly, it's a very dynamic field and very much an evolving field, just constantly trying to learn new things and reincorporate the state of the art, and staying on top of that, staying on top of that highly dynamic field. So anyway, explore the website. Again, I shared it with you. Feel free to email me, if you have questions about the program. My email is on the website. You can either email myself or our director, which is Director Perna, and email either of us. And if you have questions, and yeah, I think that's pretty much it. So again, I don't want to infringe on anyone else's time, so I guess I'll stop there. And if we have questions at the end, I'd be happy to answer them.
All right, thanks a lot, Jim. And with that, we'll move on to our final speaker, Peter, and then hopefully we'll have some time for some of the Q&A from the audience and the discussion. So Peter is an assistant professor at the University of Virginia's School of Data Science, with a very broad range of research interests, ranging from particle physics to the criminal justice system, and is a huge advocate of cross-disciplinary collaboration. And so he's been teaching at the university since 2005 as a physics PhD. And he's partnering with the School of Engineering, Applied Sciences, and the School of Medicine, not to mention the School of Business, for his efforts. So Peter, can you tell us a little bit about the efforts at UVA? And then we'll try to sort of keep this one down to, like maybe 20 minutes if possible, just so that we have some time for some interaction between you guys and the audience. Thanks.
All right. Thank you, William. Thanks everyone for the opportunity and for coming to listen. I will shoot for that mark. So let me just take a note here, so I don't run over. Okay. On a side note, my background here, it's an old Zoom background that popped up. This is actually my office from when I was at the University of Washington. So it's directly below the eScience Institute, which at the time was a library. Anyway, that's just on a side note of curiosity. Okay, so at the University of Virginia, we have several levels of degree programs. I'll focus mostly on what we're doing in the undergraduate space, but I'll mention the graduate programs briefly. We have a master's degree that's been running. The first students graduated in 2015, so that's been going for quite some time. But it is from what I call the 0th generation of data science education. So it was created by grabbing a few courses from different pre-existing departments throughout the university, and then it has grown over time off of that base and hasn't had a full refresh. We since became a school. As William mentioned, we're a school of data science, so we have our own dean. We don't have departments or any structure inside. And so that gives us some flexibility and the ability to move people around within the school to address issues, which we've been using to our advantage as we've been bringing up these new programs. We just started a PhD program as well. The first students enrolled last fall, and actually some will be finishing up within a year, from what I understand, but that's because they started in a different program and then transferred in as they were along through their program. But here to focus on the undergraduate program. And so we currently have a minor that is up and running that has about 600 students enrolled in it. It takes 5 classes to do that minor, and we allow a lot of flexibility with whatever department someone is in, or if they're in our School of Engineering, and how they go about getting to those 5 credits. So it's really trying to cast a wide range. And it also does not have a very tight requirement to push deep down the tech stack for programming or machine learning. Those are still required, but it's not something where you need to be 4 or 5 classes deep down a tree in order to make that happen. And that's been running for a couple years. So about similar in timing for the minor that we heard about earlier. On the bachelor's side of the fence, because we're a public school, we have a state approval process to go through. So the university has submitted an application and it's fully signed off by the university to launch a bachelor's degree in data science, but it has not received state approval and it is in that process. So any comment I may make about an undergraduate program is purely at the hypothetical and proposal stage. There's no official word from the state. You can catch me later and I can give you more details about the timeline off Zoom or by email or something. To sort of describe a little bit about the philosophy behind our minor and our major, what we observe is the students who are interested in studying data science at UVA come from a broad range of places and they're looking for many things. And then when they graduate, they are looking to do many, many different things after they leave. And so we didn't want to take a narrow focus. And so, for example, just focus on a small piece of data science like machine learning. And the way that we describe it is that we say we want to equip students to face the challenges of working with data at scale. That's sort of the mission. And that is a need that we see is growing across every part of wherever our students are getting jobs. A joke we sometimes say to how would you spot someone who came out of our program after they've graduated? They might be the person in the office who would say, why are you using Excel for this? That would be something that we would see as a good sign. They'd be able to recognize the challenge that the data presents and why Excel is not able to meet that challenge. To give a little more of a flavor of how we think overall about the field of data science, we teach and structure everything in terms of a data pipeline. And as things move through that pipeline, people pull on different skill sets. What we view as the most challenging part is whenever you have to move from the human side of the fence to the digital side of the fence, or back the other way. So for example, when people are in the physics context creating an experiment and deciding what model they want to use of how the universe works to capture that data and get that done, that requires mapping the infinite universe they see into some set of data structures and then dealing with the technical challenges behind making that happen. On the other way, once you've moved everything into that abstract digital space and done your computations, which you could never do with an infinite resolution in the real world, and you come back across that boundary, you have lost a lot of the context. This is something where you often see where humans are confronted with conclusions where the person who is doing the data analysis understands exactly what they're saying, and then they say it to people who didn't have their hands all the way in and were doing everything. And without that context, then things can go astray and you can have people who take the wrong interpretation or get misled. And so that's why we say that boundary both into and out of the digital world is very challenging. So I give that all as just a little preamble of how we think about data science in our curriculum and what we're trying to teach to our students. So what does that mean in terms of the structure of our curriculum? The way it works, since we are a school in our own right, is when students come into UVA, they then have to apply and transfer into the School of Data Science. So the first year that a student is at the university, they are taking, from a data science standpoint, there are 2 classes. We have 2 1000 level introductory classes, and then, you know, the host of whatever else they're doing, hopefully physics and calculus if they're like me, but you know, you never know what they'll take. My father would prefer they take economics, but don't need to go into that now. And in those 2 1000 level data science classes, what we're looking at there, since we have the 2 classes, one of them falls on what we call the systems space. And so you're looking at things like realizing how to use your computer as a tool to get the job done, which is more than just learning the programming languages that you need to use. It's understanding concepts like storage and RAM and what a CPU is, what a GPU is. The way that we tell it basically to them is, by the end of the semester, we want your computer, which in their case usually is a laptop, to sort of fit like a glove. We want them to be able just to be right into that machine, because then everything else downstream is unlocked. The other class that we have, which we call Foundations of Data Science, that is where we try to introduce them to the bigger questions that a data scientist is usually asking as they're going about doing their work. So for example, the place we start them with is, imagine your first year of college, you've been swimming with your cell phone and the data world and everything around you, and social media is everywhere. So we start asking them the questions about that system, which they know really well. So there's data privacy questions, there's how much data is going on, there's the scale, there's what are the companies collecting, how are they deciding to show something to you. That's where we make that first connection with them and try to make that connection to the human who's going to be studying data science. Then we go from there. As we move into their second and third year, they're mostly working their way through our core curriculum. There are a lot of the usual suspects you'd think of in data science class. I won't go through all of the details right now, but there's the additional thing to mention is we also have a separate math track. When we were looking at how to incorporate mathematics into our curriculum, what we found was the sequencing from the math department was focused on making a mathematician who does proofs. And the problem was that wasn't what we needed our students to be ready to do. So the first example that we give, mostly because we don't get any fight with the math department, they totally agree with us on this one, revolves around doing linear algebra on your computer. They don't get out of bed in the morning, or at least our math department doesn't, to be working with linear algebra packages and doing all that kind of stuff on the computer. And we said, we need our students to be able to do these kind of things. And so there are other examples. It's not just that one, but that's the standard one that we go to. And so in order to get linear algebra up earlier in the curriculum, we worked on our own mathematics track. It's still the same number of credit hours you would expect for a BS type degree. And the other one that I should mention is we also bring probability much earlier in the curriculum than you would normally see that in a math curriculum. And there's other stuff in the weeds, but those are really the big two. Finally, the last year of the program, what the students are really focused on is moving into a space where they are more creative. If we were to sort of put one verb to each year of the curriculum, down in the first year, they're focused on recognizing and being aware of the world that's around them. And then they progress through to the fourth year where they're creating. So for example, there's a project-based class where they have to envision and execute projects and things like this. And on the content side, now that they're done with the coursework, we're establishing a concentration-based system. So for example, right now I'm working with folks from the astronomy department and from the physics department to put together a concentration in, quote unquote, if you'll permit me, big data, where we're looking at data, for example, from a massive scale experiment of some kind. Personally, as much as it hurts me as a physicist, I'm lobbying for the astronomy data because I think their pictures are gorgeous. And I think students are a little bit more in awe of astronomy pictures. But I'm sure we'll find a way to get some LHC data in there as well or something. But then there would be other concentrations as well, but I mentioned that one because that's the one I have a hand in. I have a few more minutes, but I'm going to pull up right there, William. How's that sound?
That is awesome. So thank you, Peter, or Pete, and then thanks all of you. And let's move into some discussions. I'll alternate and from the Slido. So please, everyone, feel free to use Slido, though it's a pretty small group. And then also, like answers amongst yourselves. So one is, Sarah, you kind of teased us earlier with this idea that you have a working group where you're looking into AI in the curriculum. So, how would you distinguish preparing people for AI as compared to data science in, sort of in the educational context?
Yeah, I think that, the group is still in discussion. What they've been doing so far is just trying to understand what classes, even are in the current AI space across campus, if that makes sense, because there's on a big campus, I'm sure you guys can really, and new departments are creating courses all the time, and so just trying to understand what those look like on campus, what students have access to at the moment. I think we recognize that, or have been thought that there are certainly, like, we think of data science and AI as having a large overlapping space, particularly when we're thinking about machine learning and deep learning, but that there are areas, particularly in the robotics space, for example, which is really strong at UW, which is in AI, but not necessarily data science. And we're trying to understand, again, we'd like to create a framework that is usable across the whole of campus, but I think it's yet to be determined if that seems like either both sort of necessary or the most useful to students. And so I think one of the things on the table is really having that like an AI option may be focused within engineering, or have an option that looks a bit different coming from the engineering side versus the other parts of campus. And whether or not there could be, in terms of trying to serve the other parts of campus, some of that integrated in with the existing data science minor, or creating a related AI minor. Again, trying to, because we see certainly, and we have wonderful examples, right, currently with what's going on in the generative AI space, that there's a lot of conversations to be had in the social sciences, arts, and humanities about large language models in particular. And so we're wanting to really create something that has something for every part of campus, even if that's not through a single option or a single program. So I'm not, that was a bit of hand waving, but I think that's kind of where we're at the moment.
Okay, thanks. And I will have another question for you, which is, have any of the departments sort of worked to integrate data science throughout their curriculum as compared to offering, okay, like here's a data science, say, for physicist, or like a data visualization for social scientists, as compared to like a particular course that they sort of concentrate everything into, whether or not they change their particular curriculum to integrate data science?
Sorry, was that one for me too, William?
That one's for you too, for okay. Now.
I think different departments have taken different approaches. In some cases, people, especially some of those faculty that I pulled up that were hired in the context of sort of as data science hires, and we had a wave of those that happened about 10 years ago, and then a more recent wave associated with the minor. I think that there's been different approaches. In some cases, it's adding data science modules within existing courses. And I think that's been an approach again in departments where curriculum is really tight and it's hard to bring in at the undergraduate level whole new courses. And I think that's more common in some of the applied disciplines. So for example, in physics or biology, where that material then is added to an existing course. Versus kind of a proliferation of courses in the space that might be happening more on in the methods department. And I would say there's, again, this may not quite get to your question, but particularly in something like machine learning, we've seen an array of courses be developed even through computer science that are largely serving students outside of their discipline, as well as courses that are for the computer science majors. And so I guess I would say it really varies across different departments, but over time, as the departments recognize the needs, they are creating, for example, machine learning for biologists or machine learning in oceanography. But those courses have been slower to develop, but we are starting to see that transformation now. So I'd say over time, they're less reliant on other departments.
And here's a question for all of you, and maybe I'll start with Pete on this one. Is how do you balance the coding requirements for undergrads who who are sort of doing data science as sort of part of your program? And I imagine that this varies between all of you. In terms of like the coding backgrounds that they come in with or the coding requirements, if they are, if this is sort of like an option for them as compared to this being sort of their major, like in Jim's program.
Yeah, so I would say the first thing is that it's a little messy. You can't shy away from it. Oftentimes you'll see the students who don't have as much proficiency, they will withdraw. If it's a group environment, they'll often let the other students take the lead. And even if it's individual work, you can often see them on on an emotional level, they get sort of down, they'll beat themselves up and they'll pull back. So it's tough. That's the first thing to do, is to acknowledge that. And then the other particular piece to this kind of thing that I see is you often get people who they sort of get out in front of their skis when they're trying to pick up coding and catch up. You can do a lot with copy and paste, and now with ChatGPT or code, whatever it's called. And they often won't take the time to think through the moves that are going on or give themselves the time and the space, and they sort of get jammed up. So that's kind of how I see the challenge. Hopefully you don't have the students who are further ahead being jerks about it, for lack of a better term, if I can be brief with the note. That's a separate issue. So that kind of defines the space of the trouble that I see. And I think that instance requires more attention from the instructor. So I think the first way that you meet that is by spending time with the student, listening, so you can figure out where they are in that space and trying to identify what their objectives are, and then help them figure out what's the next thing they need to figure it out. And you got to break it down into pieces and figure out what the next step is. And it doesn't mean there's a perfect solution and you solve everything, but I think that's the basically what I would say, just in general, without seeing the specific circumstances. Acknowledge it's hard, and then identify that you have to spend some focused time on that student, helping them get a plan in place.
And Jim?
So we see that, so I guess coming from a master's program, we do kind of have an expectation of proficiency entering the program. Again, we have that boot camp, but we see the same kind of problems that Peter mentioned, where certain students in the first semester it can be really overwhelming, because like the amount of coding is non-trivial and it hits quick, like it be all at once. So we see the same exact problems where students will withdraw. Not a lot, maybe like 5% probably. We've seen like 5% or so sort of withdrawing from, it just can be a bit overwhelming, and trying to handle that in the same way, one-on-one attention, also really emphasizing like how to debug code, because that can be a huge problem with the copy and pasting, and with this Copilot as well. You can't just, like, that's not how you code, right? You don't just like put things in and all of a sudden it works, right? We really emphasize like going through it and making sure that like I always emphasize that you should never be like two or three undos away from a fully functional code that you understand 100%, right? And it's all incremental, where you're like, you build and you should be. And so like when I debug code, I always just comment the entire thing out, start at the top, start working my way through it. And we try and force students to do that as well. I think one of the best exercises is just debugging exercises, something's broken, there's 500 lines of code, find where it's broken, like why is it broken. So like we try to really emphasize that. Another thing we see is sometimes there's almost kind of different paradigms of programming. Like if you're relying heavily on packages, especially in R, I find that things get very abstracted, where it's like everything's so abstracted under the hood, which is sort of a different paradigm than like traditional programming, right? Where you have for loops and like everything is logical workflows where you're coding a lot of it yourself from scratch. And so sometimes I feel like in data science, we get maybe a little too on the on sort of the abstracted level, where one line of code is actually doing thousands of things under the, or not thousands, but many things under the hood. And so we sometimes try to dial it back and actually ask them to code algorithms from scratch, which is a great exercise to enforce that kind of logical, that sort of more traditional coding workflow. And so that's one way we kind of deal with it, is it's trying to show both things. It's not all just one-liners or with Python or whatever. It's good to know not only what the code is doing or how to use the code, but what the code is doing under the hood. Like in theory, like could you actually rewrite, say you have one line of Python code, could you reproduce that if you needed to from scratch or whatever? So that sort of thing. Maybe
it's always a tension, right? Like where, like I have students, and then depending on what they, their majors are or what they want to do, like say the undergrad or even the high school level, then, maybe it's useful to have them, do their own implementation of a neural network or something for learning. But other times, right, it's like, okay, like given what you want to do and sort of where you are, just pulling up TensorFlow or Keras or something probably gets the job done.
Yeah.
And so, there's a certain tension there, right, in terms of, sort of which way you want to go with that, depending on their career path, I would guess.
The students can be frustrated with that too, because they want the TensorFlow side, like they want the business tools that are gonna, get it up and running, like more that, because sometimes, at least you might not see this as much in maybe a computer science department or an applied math department, where the expectation is that you'll be, doing the things that you just mentioned, coding a neural network from scratch, which we do, but there's usually pushback. They kind of will say like, why, like they'd rather see it from the more, PyTorch side, Keras side, and seeing it in a more applied sense. But the problem is they usually, when they run into a problem with Keras or something, they can't debug why it's happening. Like if you don't know what the heck it's doing under the hood, it's very hard to identify. Like, okay, great, you have 500 lines of whatever workflow that cleans the data, pre-processes it, does data augmentation, and then does all these different steps. And like, there's something's not working. Your accuracy is terrible. Where is it? I think that doing the coding it yourself side allows you to be much more efficient at like laser focus, identifying it's probably something in that subroutine, or it's probably something here. So like identifying where those problems. We try to emphasize understanding as much as possible from top to bottom of the code, so that you can be an effective troubleshooter and effective debugger.
And Sarah, I mean, your program is very broad, sort of university wide, and so I imagine that this is only multiplied for you in terms of the varying levels of coding that somebody will have had in a department or at a given moment in time. And is there something that you do to try to help harmonize that? Is there like a software carpentry thing or a service course or?
Yeah, so we do have a software carpentry partnership, and so we run intro to Python and R kind of quarterly. We do. There's other groups on campus that offer R, so we tend to do Python 4 times a year and R twice a year. And so that is an avenue that people can take. We actually find that's mostly that the people who come and participate are graduate students. And I think that's because it's hard for graduate students to necessarily take a full course or, like get buy-in from their advisor to spend time, doing that. But it can be a much easier thing to convince them to just, take a 2-day course and use that to get up to speed. I will say that, certainly for like incoming freshmen, even though we have courses that are designed for students who don't have any previous programming experience, there's even the differential there, right, in students, whether or not they've had computer science in high school, and that really affects how they can do in that first level course, even though it's seen as, not requiring that. And I think, yeah, these differentials, I think, come up across the board, and as the others have pointed out, like, trying to, I think, sort of normalize that for students, that they're coming from different places and provide supports is really important. We see that in the Data Science for Social Good summer program. This is an issue we tackle all the time as well. And that's a lot of individualized kind of understanding, and just trying to, a lot of it comes down to kind of thinking about imposter syndrome and what students are experiencing, and trying to, as you say, even just surface that so that they know that they're not the only one that are feeling really overwhelmed or out of place.
Mm-hmm. No, that makes a lot of sense. And I'll just sort of go ask him. It looks like there are a couple of questions for Jim. One is a question where I think maybe you probably have this on your webpage or something, which is, sort of what books and materials you're using for your boot camp. And so hopefully that's online somewhere and you can point people to it.
So the boot camp is actually, you need to be part of the program to access the boot camp. So it is something that's going to kind of behind a password. It's sort of, we put it together ourselves, so it's kind of coming from a lot of different sources. We didn't use one textbook, but it's really just kind of like introduction. There's 2 segments: introduction to Python, introduction to R. The Python thing is more just the standard thing that you'll see in any kind of online boot camp, like just going through all the fundamental constructs. Like the first 2 weeks are, kind of Python without packages, where we do all the, if statements, try, except, while, just all the usual constructs. Then we move into, NumPy, the kind of NumPy, pandas, matplotlib, the standard, packages. So it's kind of just a crash course in introductory Python. And then the second portion is just introductory R. So it doesn't follow a textbook per se. It's more kind of more sort of in-house created. But if you look at, like, if you were looking for something similar, like a lot of the online boot camps that you'll find with, I'm drawing a blank right now, but if you just Google, like, introductory Python tutorial, you'll find half a dozen of them on a Google search right there. There's a lot of them out there. We just do it we really want to force students to work through it in some way. So there's a guided structure where we have TAs, like, it's free, and it's free for our incoming students, but it is part of like a structured course where you have TAs grading assignments, and like they have to complete it. It's sort of not 100% self-education, because in that context we usually find that it's very hard to motivate someone to do something 100% on their own without any kind of driving element that says, like, you actually have to complete this. So we try and incorporate some carrots and sticks kind of paradigm in there.
And I'll ask another one sort of for Jim and Pete that are kind of related, right? But you guys both have backgrounds as physicists, right? And so, and Craig, if you want to chime in, then this would also be useful. So the question would be is, like, when you have physicists who are entering into your program, what is it that you think that, like, is not in the physics curriculum that makes it sort of hard for them when they're starting into the data science, for those who are not, like, sort of in their copious free time, like reading books on probability, or, well, actually more likely statistics, or doing a lot of coding on the side, so for somebody more typical.
I'll jump right in, although I admit this answer might be getting a little stale. Often you see pretty weak skills with relational databases. And usually you find people who are on the object-oriented side of the fence as opposed to the relational algebra and relational database side of the fence. And so I've found oftentimes when the physicists come in, they just have trouble wrapping their head around it. I guess I should call it the object relational impedance mismatch, if I was to be as technical about it as possible, and put as many people to sleep as I could. But it's like you get the root guy talking to the slow control person, and their heads explode because they're on the other side of the fence. So that would be an example I'd give right there.
It seems too, like, there's so many different physics undergraduate curriculums as well. Like, I came from more, not a heavy emphasis on computation at all really in my undergraduate career. It was more just standard Griffiths, just standard exposure to it. And then when I went to George Mason, I did a lot more computational physics, and there you start to see quite a bit of overlap where, like, the skill sets in a computational physics curriculum, at least the applied math stuff, optimization, numerical solvers, all that kind of stuff. There you're seeing a decent amount of overlap, and also students who think algorithmically, like think very logically and break things in. They're basically able to code effectively. Whereas, at least I know, looking back, this is more myself looking at my past experience, because we don't have a ton of physics students coming in, decent number of engineers, but less so coming straight from a traditional physics program. I look back at my code in early graduate school and just think, like, I basically was just not good at coding, right? I came straight out of a physics program with, again, I could do all the Griffith stuff, all the quantum mechanics stuff, the standard stuff, but just not having those, just low on the side of how well I could code. So that was probably, at least for me, where my shortcomings were. And that, takes something that we try to really accelerate in our program, is getting that ability to code up to speed.
Okay, let's see. So another question for Sarah is, can you say a word or two about, like, has your program worked for physics departments? And if so, like, even if it's not the physics department, even if it's a bio department, did they find that there was anything that they had to sort of drop from their curriculum in order to make this work?
Yeah, that's a good question, and especially because this is a physics audience. So I will note that actually the physics department doesn't have either the undergraduate or the graduate data science options. I know that they have struggled, I think, in particularly the undergraduate option. I think the graduate option is in the works, but the undergraduate option, because of that, having to sort of trade off courses because they're already, close to the maximum or at the maximum allowable for a degree with their existing courses. And so I think that's kept them from instantiating the option, just to be honest. And that's true of a number of departments. And that was part of the impetus for creating the data science minor. But I think the challenge there is the data science minor is really designed to not be as focused on data science skills. It's a mix of data science skills and data science studies. And so I think for physics majors, it would be a better fit to be including that rigor. I think what has tended to happen is kind of what is that data science kind of work has been incorporated into their existing courses. That's been a more common pathway. But yeah, I would say I think it is a struggle, and I think it would be great to have the folks from physics. I haven't talked to them in a while, So this is sort of spawning me to think, go back and check with them and see if there's, you know, how that's moving along in terms of, because I know there's interest in trying to accommodate this, and so much, I mean, interest from the faculty, but so much interest from the students, because like others have said, that our students really see having data science skills training as an asset going out into the job market, and particularly in our area in Seattle. Those skills are really advantageous, and you know, can really make somebody's career. So,
I'd like to just comment on that. That's an excellent point. There's sort of two trajectories, right? Like if you're trying to become an academic physicist, that's a very different than someone with a physics undergraduate degree who's trying to transition into the tech industry or something like that, right? Like they're two very, and like most of our students are on, they're trying to get jobs in industry. They're not really trying to be academic physicists. Like they're not trying to publish in physics journals. They're trying to get a job at, you know, some tech company or something like that. And sometimes you'll get, I've incorporated physics elements into courses and actually got a decent amount of pushback where they're sort of like, why are we doing this? Like this, I'm not trying to be a physicist. I don't want to. And so like, there's a tension there, and it's sort of almost requires two different solutions, right? Where if you have to try and treat the two different cases differently, right? If you have physics students who their career goal is to be a physicist and to work in academia, that probably would suit like the minors and those kind of things, like you mentioned, right? Like you have those minors, that sounds like a perfect fit for that kind of thing. Whereas for our program, it's more of for someone who has a physics degree and probably maybe wants to transition into industry, right? That might be better suited for a master's degree or something like that. So probably having that information up front where which of these different trajectories is best suited for your career goals in the long run for the students. So it's difficult, and it's hard to
Keeping
know.
in mind that most physicists, right, are not going to become professors when they grow up. I mean, this is just a numbers game, right? You know, it's not going to happen, you know, though many may still do physics in industry, or they may switch over and do something that is more, you know, data science. And I'm sure we all have friends who have gone either way. We're drawing to a close, but I'll ask, you know, sort of one other question that's sort of related to this, right? Which is, you know, like at your universities, while I imagine that there are departments that are apathetic about data science and, you know, like sort of bringing it into their programs, are there any that are outright hostile, or is this something that you've had to face where you have people who are like, well, no, this is a black box, we don't want this, you know, like, why are you trying to get this in, you know? So has there been any pushback, you know, sort of at the, you know, either at the departmental level or in some cases, against sort of updating things or doing these sorts of integrations?
I haven't felt really any pushback aside from that some of our content overlaps with CS department, but it's not really, it's more of a complementary thing. I haven't really experienced any like hostility or tension but again, I don't know about Pete or Sarah.
Yeah, do you want to do this on the record while it's still recording?
We'll take the recorded version first, you know. I'll let you know when the camera's off.
I'll say this. So at UVA, the way the funding works is a student pays their tuition, and then the tuition money gets doled out based off of the school that puts on the classes that they take. So if you took all your classes in our School of Data Science, then the School of Data Science will get all your tuition dollars. It's a little more complicated than that, but first order. And so with us looking to have a major, that is going to take a lot of credit hours, and they have to come from somewhere. It's a conserved quantity. UVA said they're not looking to increase the enrollment. And so no one has come up with a objection based off of academic grounds. There are certainly, if people think this will cause money to flow away from them and flow towards us, the people who have concerns on financial grounds. It is what it is. What can I say?
Yeah, I guess I'll just say that, the structure of having the options that are owned by the home department really helps build camaraderie, because what I'm often say to them is this is a way for you to keep your students by like adding on, you're able to show them that you are responding to, to adding data science to what they're picking up, and so that they're not going to lose them to another department that's doing data science. They can build this into their own curriculum in a way that's meaningful for their discipline. And so that, I think, has helped to build that kind of collaborative spirit on campus.
I think the minor, I mean, that has to be like a very attractive thing, right? A minor in data science sounds like a excellent attachment to almost any degree. Like I could imagine that being very popular.
Yeah, and there's a lot of pathways through the minor. So if you really want to take, like really focus on the skills, you can do that. And anyway, I think it allows for a lot of flexibility too, for like you're saying, like depending on what the student wants to do coming out of their degree.
And then also, Pete had mentioned how, like the typical physicist probably has not seen SQL, much less NoSQL, or heaven forbid, a vector database or some such thing, right? And chances are probably won't, right? But that might be another great option for a minor, right? Where, like there could be options that really don't form, sort of like a core part of the physics curriculum. But if you wanted to be a practicing data scientist in industry, there's no way you're going to survive without it. And for some particular applications in physics, it's useful, but by no means all, even at this stage. So like, I think that that's something where that could also be an attractive option. Let's see. So I want to be respectful of people's time. We are 2 minutes over, so not bad. Thanks again for all of you for participating on the panel. We can stop the recording and we'll go ahead and put this up on YouTube once it processes, and then we'll hope for the long tail for viewership. Thanks again.